We often picture physics labs as these sterile, white rooms packed with lasers and supercomputers, right? But the truth is, some of the absolute biggest, most fundamental questions in science just can't be answered here on Earth. To truly understand the fabric of reality, we literally have to look up. So, welcome to this explainer, where we're going to explore how some of the most extreme objects in the universe actually function as nature's ultimate laboratories. For over a century now, Einstein's general theory of relativity has been the absolute pillar of modern physics. But physicists are always out there looking for cracks in the foundation. To test the extreme limits of Einstein's gravity, and to figure out if maybe some alternative theories might actually hold up in ultra-strong gravitational fields, we need an environment way more intense than anything in our own solar system. Which brings us to a massive question. How do you actually test gravity in the most extreme environments in the universe? Well, the answer is the binary pulsar. Imagine a cosmic clock, but one that is mind-bogglingly precise, just tearing through an intense gravitational field. When you take a rapidly spinning, highly magnetized neutron star that's blasting beams of radiation across the cosmos, and you lock it in a tight orbit with another massive object, you've basically just built a dynamic laboratory. This setup lets us measure space-time itself with a level of precision that is, honestly, just wild. We have a fascinating roadmap for today. We'll start with nature's perfect cosmic clocks, then look at surviving two supernovae. Third, testing Einstein's gravity. Fourth, the double pulsar breakthrough. And finally, from mergers to new physics. Let's jump right into Section 1, Nature's Perfect Cosmic Clocks, the Fundamentals. So there's actually a massive difference between a lone, isolated pulsar and a binary pulsar. Now, an isolated pulsar is an amazing object all on its own. It's a collapsed stellar core that just sits there spinning and emitting these highly regular pulses of radio waves, but it is essentially just flying solo. A binary pulsar, on the other hand, is locked in this intricate gravitational dance with a companion. By recording the exact times those pulses arrive at our telescopes and comparing them with deterministic timing models, astronomers can spot what we call timing residuals. These are tiny, tiny variations that encode every single unmodeled physical effect, everything from the tug of that binary companion to a passing gravitational wave. But finding these specific laboratories is definitely not easy. Out of over 1,500 known solitary pulsars, only a really tiny fraction belong to these dynamic binary or recycled systems. In fact, for the first 7 years after pulsars were even discovered, we only found solitary ones. People literally started to think that the supernova explosions creating these pulsars were just completely destroying any binary system they happened to be in. But thankfully, nature is a little more creative than that. As it turns out, binary pulsars come in several unique flavors, and the type of companion star totally dictates the kind of physics we can study. You've got systems with massive main sequence stars or totally dead white dwarfs. You even have these wild ones called black widows. These are locked in sub-day orbits and literally evaporate their tiny companions with intense radiation. It's crazy. And then you have the absolute holy grail for gravitational physicists, double neutron star binaries. These feature super short periods, highly eccentric orbits, and just incredible relativistic speeds. Which brings us to Section 2, Surviving Two Supernovae, a Violent Origin Story. Okay, so creating a double neutron star system requires a highly specific, honestly almost miraculous sequence of events. The whole evolutionary journey kicks off in a massive binary star system. The heavier star evolves first, explodes in a massive supernova, and leaves behind a neutron star. Fast forward a bit, and its companion star starts aging. It swells up into a bloated red giant or supergiant, expanding way beyond its normal boundaries. Material then starts spilling from this bloated star directly onto the neutron star. We call this the high-mass X-ray binary phase. And here's the cool part. All this falling mass actually spins the neutron star up to incredible speeds, effectively recycling it into a millisecond pulsar. But then comes the make or break moment. The companion star's core collapses, triggering a second supernova explosion. Just whoomph! Unimaginable force! Normally, the sudden loss of mass and the asymmetric kick from a colossal blast like this completely breaks the system apart, sending two solitary stars just flying off into deep space. For a binary pulsar to actually form, that kick has to be perfectly aligned and perfectly balanced so it doesn't shatter their gravitational bond. And yet, against all astronomical odds, in very rare cases, the binary survives. The result is a double neutron star system. You've now got an incredibly fast, recycled millisecond pulsar and a younger, slower spinning pulsar, both bound together in a really tight eccentric orbit. Just like that, our pristine, point-mass cosmic laboratory is completely assembled and ready for testing. Moving on to Section 3, testing Einstein's gravity, the post-Keplerian framework. So in basic physics, we use Kepler's laws to describe how orbits work. But when you're dealing with strong gravitational fields, those classical laws just don't cut it anymore. But don't worry, instead of getting bogged down in brutal tensor calculus, astronomers look at what are called post-Keplerian or PK parameters. Think of these as the measurable glitches in our cosmic clocks. We can measure how much the orbit rotates, known as periastron advance. We can measure how time actually dilates for the pulsar. We can measure the orbit physically shrinking. And we can even measure the delay of light itself. Here's why this matters. If we can measure just 2 of these parameters, we can figure out the exact masses of the 2 stars. If we can measure 3 or more, we can strictly test if Einstein's predictions were right on the money. One of my absolute favorite concepts here is the Shapiro delay. Since both components are point masses, these relativistic effects aren't polluted by messy tidal forces. Imagine the pulsar swinging behind its companion from our point of view here on Earth. Its radio pulses literally have to travel through the curved spacetime generated by that companion's mass. Shapiro delay practically lets us map out those invisible dents in spacetime simply by timing how long a radio pulse takes to climb out of that gravitational well and finally hit our telescopes. And we know for a fact these measurements work flawlessly. Discovered back in 1974, the famous Hulse-Taylor binary pulsar was an absolute game-changer. By timing it over several years, astronomers noticed the orbital period was slowly decreasing. The orbit was shrinking at the exact rate predicted by general relativity due to the emission of gravitational radiation. It was the very first indirect, but totally conclusive, proof that gravitational waves exist, decades before we ever detected them directly here on Earth. Now for Section 4, the double pulsar breakthrough, J07373039. The 2 halves of the double pulsar system, officially known as J0737-3039, are just staggering. It is the first and only known binary where both neutron stars are observable as radio pulsars. Pulsar A is an older, mildly recycled pulsar spinning every 22.7 milliseconds. Pulsar B is the younger companion, spinning way slower at 2.77 seconds. They interact in a remarkably tight 2.45-hour orbit, just whipping around each other at staggering velocities of over 300 kilometers per second. Because we can track the pulses of both stars at the exact same time, the constraints we can put on physics are totally unprecedented. To really put into perspective just how extreme this laboratory is, let's look back at that periastron advance parameter we talked about earlier. In our own solar system, the orbit of Mercury shifts by a tiny, tiny fraction of a degree every century due to the sun's gravity. But in the double pulsar system, the extreme gravity causes the orbit to rotate by nearly 18 degrees every single year. That's a relativistic effect 140,000 times stronger than what we see with Mercury. I mean, at this level of precision, scientists even have to account for how the spinning neutron star literally drags the fabric of spacetime around with it, a wild phenomenon called frame dragging. Finally, Section 5, From Mergers to New Physics, the Future. Because these systems are constantly throwing off gravitational waves, their orbits are ultimately doomed. The relentless emission of these spacetime ripples slowly drains away their orbital energy. Step by step, the 2 neutron stars will inevitably spiral inward over millions of years. Eventually, they will violently merge. This catastrophic coalescence can produce a massive kilonova explosion, forging heavy elements like gold and ultimately resulting in a collapse right into a black hole. In fact, discovering the double pulsar drastically increased our estimates for how often these explosive events actually occur in the universe, which is absolutely vital information for modern gravitational wave observatories. But before they merge, these systems act as strict, uncompromising judges for the fundamental laws of nature. While general relativity works beautifully, there are alternative frameworks out there, like scalar tensor theories, that agree with Einstein perfectly in weak gravitational fields, but might behave totally differently in strong ones. By measuring these orbital parameters, binary pulsars allow us to test the equation of state, which is basically us trying to figure out what kind of bizarre, exotic matter actually exists inside a neutron star's core. This allows us to place severe restrictions on those alternative theories. So I want to leave you with this thought. Right now, Einstein's theory remains completely undefeated. But physics thrives on finding the anomalies, right? As we build better telescopes and uncover more of these perfect cosmic clocks buried deep within globular clusters or scattered across our galaxy, we are going to push our tests to even greater extremes. Could one of these binary pulsars eventually be the thing that reveals the cracks in our current understanding of the universe? It's a thrilling possibility for sure, and one that absolutely keeps astronomers looking up. Thanks so much for joining me on this explainer, and I hope you walk away with a newfound appreciation for these incredible cosmic laboratories.